In the Pennsylvania blast furnace district in the early 1900s, a maintenance worker entered a Cowper stove on a scheduled inspection. The purge valve had been open the required interval. The procedure said the vessel was safe. The man did not return. A second man sent to check also collapsed. The accident report said he was overcome by gas. The procedure was not changed. But to understand how a 100-foot pressure vessel became a place men died from something they could not see, smell, or taste, you have to start with what it was built to do. If you are new to Steel and Sweat, this channel covers the machines and the men of American industrial history, the things that built the country and the things those things cost. Subscribe and leave a comment with the next story you want us to dig into. To understand the hot blast stove, you have to start with the problem it solved. A blast furnace in the 1850s was already one of the most productive industrial machines in America, but it was thermally wasteful in a specific and expensive way. That waste had a direct cost every ironmaster tracked: the quantity of coke consumed per ton of iron produced. Coke was purchased, transported, and charged into the furnace at real expense. Every pound of it spent heating cold incoming air rather than reducing iron ore was a pound of fuel cost that could, in principle, be eliminated. The air blast that drove the combustion inside the furnace stack entered cold. Ambient temperature air, pumped in at volume by blowing engines, had to be heated by the burning coke inside the furnace before it could participate in the smelting chemistry. That heating process consumed coke that could otherwise have been reducing iron ore. It chilled the lower zones of the furnace stack. It slowed the process and raised the fuel cost per ton of iron produced. James Beaumont Nielsen had identified this problem in Scotland in the 1820s and patented a solution in 1828. If you preheated the air blast before it entered the furnace ran hotter, consumed less coke per ton of output, and produced iron faster. Nielsen's original design ran the incoming air through cast iron pipes heated by an external furnace fire. It worked. Fuel consumption dropped significantly in the Scottish ironworks that adopted it, and the principle spread quickly across British iron production. But Nielsen's design had a ceiling on how hot it could push the air blast. Cast iron pipes heated by external fire could not sustain the temperatures that would have maximized the furnace benefit. The air went in warmer, but not warm enough. The solution to that ceiling came from an English engineer named Edward Cowper in 1857, and what Cowper designed was not an improvement on Nielsen's approach. It was a different principle entirely. Nielsen had heated the air through a surface. Cowper stored the heat in mass and let the air retrieve it directly. The distinction sounds technical, but its consequences were enormous. Where Nielsen's design had a ceiling imposed by the limits of cast iron pipe under external heat, Cowper's design had a ceiling imposed only by how large you were willing to build the vessel and how hot you were willing to fire the brick. American ironmasters, running blast furnaces in competitive markets on tight fuel budgets, answered that question by building the stoves as large as the ironwork could support. Cowper's stove was a regenerative heat exchanger. Instead of heating the air through a pipe wall, the stove stored heat in mass. The interior of the vessel was filled with refractory brick laid up in a checkerwork pattern. Millions of small passages stacked in a grid, creating an enormous surface area of heated ceramic material. During the gas firing cycle, blast furnace byproduct gas burned inside the stove and heated the brick to above 2,000 degrees Fahrenheit. Then the gas was shut off, the air blast was redirected through the stove, and the air flowing through all those small brick passages picked up the stored heat directly. By the time the air reached the furnace TURS, it was at 1,400 to 1,800 degrees Fahrenheit. That was not a refinement of Nielsen's result. It was a transformation of it. The scale. American ironmasters built these vessels too by the 1880s is worth sitting with for a moment. A standard Cowper stove in a Pittsburgh area blast furnace complex stood 80 to 100 feet tall, with some installations reaching 120 feet. The diameter ran 20 to 25 feet. 3 or 4 stoves cycled in rotation on every furnace. One sat on blast, pushing preheated air to the TURS, while 2 or 3 sat on gas, their checkerwork being reheated for the next cycle. The rotation turned over every hour or two, depending on furnace demand, and it ran continuously, 7 days a week, for the entire operating campaign of the furnace. Standing outside a blast furnace complex in Pittsburgh in 1895 and looking at the stove battery, you would have been looking at 3 or 4 cylindrical steel vessels taller than any building most Americans lived or worked in. They had no windows, no visible moving parts. They sat adjacent to the furnace stack, connected by ducting at the top and valving at the base. And from the outside, they gave almost no indication of what was happening inside them. The stove battery ran continuously. During a normal production cycle at a large Pittsburgh furnace, the 3 stoves in the battery cycled through their rotation with no pause and no shutdown between them. One stove would come off blast, the valves would shift, and within minutes the next stove in the rotation would take its place, delivering preheated air to the tuyères. The furnace never received cold air. The production never stopped. From the outside, the transition between stoves was nearly invisible to anyone not watching the valve positions. But inside the stove that had just come off blast, conditions were changing rapidly, and not in ways that made it immediately safe for a worker to enter. The gas cycle that followed a stove's removal from blast began immediately. Blast, furnace top gas from the furnace stack, was directed into the stove burner, and within minutes of the transition, the interior of the vessel was filling with a fuel gas that was roughly a quarter carbon monoxide. The checkerwork was being reheated. The vessel was, by design, a sealed chamber full of combustion products and hot gas. The question of when it became safe for a person to enter was not a question the stove answered for you. It was a question the maintenance schedule answered, and the schedule was built on assumptions about how quickly the gas displaced during a purge cycle. Inside, the temperature at the top of the dome during the gas cycle was above 2,000 degrees Fahrenheit, sustained by burning a gas that most people on the street outside would not have been able to identify. Blast furnace top gas, the byproduct, vented from the top of the furnace stack as iron ore, coke, and limestone reacted in the smelting zone, was the fuel. Low calorific value, produced in enormous volume, available essentially free as a plant byproduct. It piped directly from the furnace top to the stove burners without any requirement to purchase or transport fuel. For a blast furnace operation running on tight margins, that free fuel was a significant operating advantage. But blast furnace top gas was roughly 25% carbon monoxide. Carbon monoxide is colorless and odorless, slightly lighter than air. At concentrations of 200 parts per million, sustained exposure over several hours produces headache and disorientation. At 800 parts per million, exposure over 3 hours produces convulsions. Above 1,200 parts per million, it is immediately dangerous to life. A stove interior that has been running on blast furnace gas for a 40-minute firing cycle contains carbon monoxide concentrations that would render a person unconscious in under 2 minutes. The purge procedure was supposed to clear that gas before any worker entered. Close the gas valve, open the air purge connection, allow the air to displace the combustion byproducts, wait for the prescribed interval, then the stove is declared safe for entry. That procedure had a physical logic to it, and under ideal conditions, it worked. But carbon monoxide is lighter than air, and in a cylindrical vessel 100 feet tall, lighter than air gas, does not distribute evenly during a purge. It stratifies. The lower sections of the stove, the sections through which a worker descending from the top manhole would pass on the way to the checker work, could read within safe limits on any surface level test. While the passages above retained lethal concentrations in pockets the air purge had not fully displaced. There was no portable carbon monoxide detection technology available to American blast furnace workers before the 1910s. A Davy safety lamp could indicate the presence of combustible gas in a coal mine by the behavior of its flame, but a Cowper stove during a purge cycle was not a coal mine. The carbon monoxide concentrations present were not necessarily sufficient to affect a lamp flame, and the specific instrument that could have given a worker a number rather than a color was not yet a practical tool. The assessment was sensory, A worker would smell for gas, watch for any discomfort in the throat, look for any indication that something was wrong with the atmosphere inside the vessel. Carbon monoxide gave none of those indications. It gave nothing. The man who walked in felt normal until he did not. Imagine being the man outside, waiting for the inspection crew to come back up. If you work in industrial maintenance and recognize this kind of hazard, leave a comment below. The accident pattern across Pennsylvania, Ohio, and Illinois: blast. Furnace operations between 1890 and 1920 is documented in state factory inspection reports, in the publications of the American Iron and Steel Institute, and in the accident records that larger operations were required to submit under increasingly specific state reporting requirements as the period progressed. The sequence is consistent enough across reports from different states and different companies that it reads less like a series of isolated events and more like a single failure mode running on a loop. Worker enters the stove during a purge window. The worker collapses at some point between entry and the interior inspection target, sometimes near the bottom of the descent, sometimes deeper in, depending on where the carbon monoxide pocket had concentrated. The worker does not return in the expected time. A second worker is sent to check. The second worker, descending into the same atmosphere, encounters the same gas before reaching the first man, and also collapses. In a significant number of the documented cases, a third worker was sent in before the crew outside fully understood what they were dealing with. Rescue attempts accounted for a meaningful share of the total casualty count in these events. If you find this as important as anything we have covered on this channel, go ahead and subscribe now and leave a comment with the next story you want to see. The official reports filed after each event typically named the cause as overcome by gas or asphyxiation by blast furnace gas, which was accurate as far as it went. What those reports almost never named was the specific failure in the purge procedure, the stratification problem, the inadequacy of a sensory check as a carbon monoxide detection method, and the fact that the prescribed purge interval was derived from experience rather than from any measurement of actual carbon monoxide displacement in a given vessel geometry. Each event was filed, each event was closed, and the procedure that produced the next event remained unchanged at the next plant in the next state when the next scheduled maintenance window came around. But the thing that made this particular failure persistent was not negligence in any single company or any single foreman. It was a structural feature of how atmospheric hazards were understood and regulated in American industry during this period. State factory inspection laws in the 1880s and the 1890s had been built around the hazards that had produced the most visible casualties in the decades before: unguarded machinery, boiler explosions, mine roof collapses. Those hazards had physical signatures. You could see an unguarded flywheel. You could inspect a boiler's pressure relief valve. A mine roof inspector could test the rock with a bar and hear the difference between solid ground and a loose section. Atmospheric hazards were a different category of problem, and the inspection apparatus that had been built around visible mechanical hazards did not map onto them cleanly. A factory inspector visiting a blast furnace operation in 1895 could observe that the stove shell was sound, that the valve connections were properly gasketed, that the external gas piping was in good repair. He could not observe whether the purge procedure being used was actually clearing carbon monoxide to safe concentrations in every section of the vessel interior, because no one in the industry had instrumented that question. The procedure said, "Wait this interval." Experience said that interval had worked before. Neither said anything specific about the stratification physics in a 100-foot cylinder. The men who died in those stoves were not the furnace keepers or the blowing engine operators at the top of the blast furnace labor hierarchy. They were maintenance workers, refractory bricklayers, inside laborers. These were the men who went into the vessel on scheduled cycles to inspect the checker work for cracking, to replace damaged brick sections, to check the dome and the connection points. Lower paid, less likely to appear by name in any company document that survived, more likely to appear in an accident report as an occupation rather than a name. Maintenance, laborer, inside repair, stove man. The physical scale of what those men were working inside is worth being precise about. A Cowper stove at the Carnegie Steel Works in Braddock, Pennsylvania, or at the Illinois Steel Works in South Chicago stood between 90 and 110 feet tall. The interior, after the checker work had been fired through multiple campaigns, was a space of intense residual heat even during a purge cycle. The brick retained temperature for hours after the gas was shut off. The worker descending through the top manhole entered a confined, dark, radiating interior that had been above 2,000 degrees Fahrenheit within the previous hour, carrying a lamp, making his way down through brick passages that had been designed to transfer heat to air, moving through them not to be traversed by a person. The task was necessary. The checker work degraded with every thermal cycle. Brick cracked under the stress of repeated heating and cooling, sections collapsed and blocked the gas passages. The dome surface deteriorated from the direct impingement of the burner flame. The heat transfer efficiency of a stove dropped measurably when the checker work was damaged, and a blast furnace operation running on tight margins felt that drop as reduced blast temperature and higher coke consumption per ton of iron. The inspection could not be deferred indefinitely. The repair work, when the inspection found something, could not be done from outside. The men who did this work carried oil lamps into vessels that had been above 2,000 degrees an hour before they descended. The checkerwork passages were narrow. The brick surfaces were still radiating heat. The air, when the purge had worked correctly, was breathable. But the men working inside the stove were working by feel and by lamplight in a confined space, in residual heat, with no direct communication to the crew outside except by shouting through the manhole they had entered through. A worker who lost consciousness inside the stove checkerwork was not immediately visible to anyone. The crew outside knew how long the inspection was supposed to take, and what they could not see was often unseen until it was too late. When the time ran over, that was the first indication that something had gone wrong. By then, the window for a straightforward rescue had already closed. The crew member who went down to check entered the same atmosphere. The second rescue attempt compounded the same error as the first. In the documented cases where rescue attempts added casualties to the initial event, the pattern was consistent. The crew outside did not know they were sending men into a gas atmosphere, because nothing about the stove's external appearance told them that. The valves were in the correct positions, the purge had run its prescribed interval, and the procedure said the vessel was safe to enter. Federal oversight of industrial atmospheric hazards developed slowly. The Bureau of Mines, established in 1910, focused its early work on methane and coal dust in mining operations, the hazards that had produced the Monongah disaster and earlier disasters. Blast furnace operations, as above-ground facilities, sat in a different regulatory category. The specific application of carbon monoxide monitoring and procedure standards to hot blast stove maintenance came incrementally through insurance actuarial pressure, state regulatory updates in the major steel-producing states, and the gradual adoption of portable electrochemical carbon monoxide detection instruments after those instruments became practically available in the 1910s, but there is a specific reason the accident pattern repeated across 3 states and 30 years without producing a change in the underlying procedure, and it is worth being precise about it. The accident reports filed after each stove death were state documents. They went to state factory inspection offices. The factory inspection offices in Pennsylvania, Ohio, and Illinois were not exchanging reports with each other in any systematic way during this period. A blast furnace operator in Cleveland had no mechanism by which the accident record from a Pittsburgh operation would reach him as a document he was expected to read and respond to. Each event was processed in isolation in the state where it occurred by an inspection apparatus that was tracking compliance with state regulations, not looking for patterns across the industry. The men running those operations were not indifferent to worker deaths. Some took individual steps after individual events. But the information architecture of the period did not produce the kind of aggregated pattern recognition that would have forced the question of whether the procedure itself was the problem rather than the individual workers who had died following it. The stoves themselves are still in use, and they remain among the largest pressure vessels in routine industrial operation anywhere in the world. Modern blast furnace operations run Cowper stoves on the same regenerative principle Cowper patented in 1857, built larger and instrumented continuously, with atmospheric monitoring throughout any maintenance window and confined space entry procedures that require air testing at multiple heights before any worker descends. The physics of the hazard has not changed. Carbon monoxide still stratifies in a tall cylinder during a purge. The checkerwork still has to be inspected. The men still go in. What changed is that the procedure now measures the atmosphere, rather than assuming it. The workers who died in those stoves in the Pennsylvania blast furnace district and elsewhere from 1890 to 1920 in the Ohio Valley and in the South Chicago steel complex left almost no recoverable record. The accident reports name an occupation and a date, sometimes a plant, rarely a full name. The reports were filed by state factory inspectors who were documenting events, not investigating the procedure that caused them, and the procedure that caused them ran unchanged from plant to plant, because no one was comparing the reports across state lines. No federal agency had jurisdiction over atmospheric hazards in above-ground steel facilities, and each company closed each event as an isolated incident. What those men understood, working the hot blast stove battery on the maintenance rotation, was that the vessel they were entering had been at 2,000 degrees an hour before and was fueled by a gas they could not detect with any of their senses. What the procedure told them was that the interval had passed and the vessel was safe. The interval was a guess, dressed as a standard, and the gas did not distribute the way the guess assumed. 2,000 degrees and an invisible gas made that guess deadly. The men who did the refractory work inside those stoves were skilled in a specific and physically demanding way. Reading the condition of checkerwork brick by lamplight, identifying which sections were cracked and which were sound, estimating how much of the passage grid needed to be relined before the next firing cycle, doing that work in residual heat inside a cylindrical vessel with a single entry point. These were not tasks that could be assigned to an unskilled laborer with no experience inside a hot blast stove. The men who did this work knew the stoves. They had been inside dozens of them. They knew how the brick deteriorated, knew how the dome looked after a long campaign, knew which parts of the checkerwork took the hardest loading from the burner flame. What they could not know, with the instruments available to them in 1900 or 1905 or 1910, was whether the atmosphere in a specific stove on a specific day had actually cleared to the level the procedure assumed. That knowledge required a number. They had no instrument that could give them a number. They had the procedure, and the procedure had been followed, and the man who had followed it did not come back up. The Cowper stove worked exactly as Cowper designed it. It preheated the blast, it reduced coke consumption, it made American iron production cheaper and faster and more competitive. The men who kept the checkerwork in repair so it could keep doing that are in the accident reports. They are not in the production records. Worked is what the stove did. The people who made it possible are only on the margins of the ledger. The hot blast stoves at every major American blast furnace ran for 40 years on a maintenance procedure that the accident record said was killing people. If you want to keep following the stories of what that era cost the men who worked inside it, subscribe to Steel and Sweat.